Okay, so we have two new tests for looking at convergence of infinite series. The first one is the direct comparison test. So we have a couple problems here that involve the direct comparison test, and we'll see what that is here in just a second once we get the examples written out. So that's our infinite series. And what you want to do when using the direct comparison test, you can come up with a function that is always less than this, or always greater than this, and if that one converges, then you're in good shape. So a lot of times you have these situations where you have some kind of function plus a constant, and so if you get rid of the constant, so this would be the series a sub n is this, and this would be the series b sub n. And because this number, whatever you get here, is going to be positive anyway. This is positive, so when you add 2, this is going to be a slightly larger number than that number. And as a consequence, this, we can always say that a sub n is always less than b sub n. And because of that, you can use the direct comparison test, which basically says now, if this converges, then this converges. Because if something bigger converges, then something smaller has to converge as well. At this point, you can use any of the tests that we have already used. So this is one of these. I think it's the p-test, if I remember correctly. So if you go back to page 619, you see you have 1 over n to the p. So p in this case is 2. So using the p-test, what we have is p is equal to 2, and what we found out, what we know is that if p is greater than 1, then it converges. So in this case, p is greater than 1, so 2 is greater than 1. Therefore, the infinite series b sub n converges. So use the p-test to do this function, and then as a consequence, using the direct comparison test, a sub n also converges. And I think I'll be saying that, so I'm going to group all that together so I don't have to write it out. Okay. So since this converges because this is always greater than that. Okay, problem number 7. So I have a similar situation. Summation from n equals 0 to infinity of 1 over 3 to the n plus 1. So we'll call that a sub n summation of a sub n. So again, if we get rid of the 1, so if we let the series, this series, equal we get that. Now what test can we use to do that? Well, this is the same as, you might think it's a p thing, but that's when you have n as the base, but here we got 3 as the base. So because we have 1 in the numerator, you can make this 1/3 to the n, because 1 to any power is 1. And as a consequence, this is a geometric series. So we can say the summation of b sub n is a geometric series. and it converges if the exponent, if n is, so let's go back and look at it. I'm pretty sure this one works, but let me go back to section 9.2, which is where we talked about geometric series. I think that's the one we talked about. Maybe it's the next, oh, here we go, yeah. Page 608. So we have A, which in this case is 1, R, so we're using, this thing is actually R. This is the ratio. And it converges if R is inside these limits. So the absolute value of R is between 1 and 0. So it converges if R is in this range, and since R equals 1/3, B sub n, this alternative form. So since R is 1/3, the second series converges because it's a geometric series. So now we'll copy that, copy, and then we'll add a page, and we'll paste. Oh, something happened here. My little copy thing didn't work. Copy. Okay. Paste. As a consequence, using the direct comparison test. Actually, it is the direct comparison test. So once we know this converges, then we can use the direct comparison test to say that this converges. And I guess that should be summation sign here. The series converges. Okay. Now we go to 10. And what we have here is the summation from n equals 1 to infinity of 1 over the square root of n cubed plus 1. So again, that is our A sub n series. So we'll let the B sub n series equal the summation from n equals 1 to infinity of 1 over the square root of n cubed, which we can write it as a complete fractional exponent. So we have 1 over n to the 3/2 power. And that is a p-type situation. So using the p-type series, if t is greater than 1, the series converges. And so B sub n converges. This series converges. So so this series converges. B sub n converges. And A sub n is always less than B sub n, which I didn't put in the previous one, but this is always less than that because it's the same thing except you add 1. So the denominator is slightly bigger. N is positive, so we're going to have a positive number. As a consequence, using the direct comparison test, A sub n also converges. And the last one of these examples so can we think of a, A sub n is e to the minus n squared. So if we let b sub n equal e to the minus n, if you remember this function e to the minus n looks like this, goes through 1, and what would happen is e to the minus n squared would actually even be steeper, and it would go like this, and it would always be less than. So since the red curve, so we can say so, a sub n is always less than b sub n. So in this case, what we'd use is the integral test. So we would take the integral from 1 to infinity of e to the minus x dx and see if this converges. And if that converges, then the series converges, this series converges. So our series, our second series here, is going to be the summation from n equals 1 to infinity of e to the minus n. So if this converges, then that converges. If that converges, then that converges because of the direct comparison test. So this is using the integral test. So we always have to use another test to evaluate the b sub n series, and then use the direct comparison test to then make the second conclusion. So what we have here is the limit as b goes to infinity of the integral from 1 to b of e to the minus x dx. And so when you integrate this function, you get minus e to the minus x, and you evaluate that between 1 and b. So what I've done here is u is negative x, so when I take dx I get negative du, I get negative dx. So that's where the negative sign comes from. And the integral of e to du is e to du. So that's how that works. We did a problem similar to this before. So now what we do is we plug in the limits. So we get minus e to the b, and then we subtract minus e to the minus 1 power. And when we let b go to infinity, this is actually minus b. When you let b go to infinity, you get e to the minus infinity, which is 0. So this term goes to 0, and this term just stays what it is, which is e to the minus 1 power. And these negatives cancel out, but that exponent stays the same. So when you do the limit, that's what happens. So you just get 1 over e. So what we can say is this second series, which was e to the minus n equals 1 to infinity, converges due to the integral test. And then we paste our little statement in there. Let me go do that again. So b sub n, summation of b sub n, which is summation from 1 to infinity of e to the minus n, converges due to the integral test. As a consequence, using the direct comparison. So the second group of problems in section 4 are this limit comparison test. So that's good to know. We can use whatever we want to use. Actually, we know exactly which test to use. At some point, we have to kind of figure out which test is appropriate without somebody telling us, but we don't have to do that yet. Okay, so let's open our books and look at the limit comparison test. It says if the limit as n goes to infinity of a ratio of two functions equals L, then either the both series converge or don't converge. So what we're going to do is again, we're going to call this series A sub n. So our V sub n series would be equal to 2 over 2 over 3 to the n. Okay. So A sub n is 2 over 3 to the n minus 5, and V sub n is 2 over 3 to the n. And so if you take the limit of that ratio of those two functions as n goes to infinity, so what do we get there? Well, you can take the denominator and take the reciprocal of it. So you'll have 2 over 3 to the n minus 5 times 3 to the n over 2. And those cancel out. So we get, as n goes to infinity, you get 3 to the n divided by 3 to the n minus 5. So as n goes to infinity, what the heck are we going to do here? So what will happen is this term, once n gets large, this term becomes insignificant. And all you're left with is these two terms, which will cancel each other out, and you get 1. So that there is a limit for this particular ratio. So all we have to prove is that this function V sub n actually converges. So what we would do is we would look at the this function, and we could use the geometric series test. So let's take that and put it in a form where we can apply whether it works or not. So what we would do is take 2 times 1 over 3 to the n, which is the same as 2 times 1/3 to the n. And since r, which is this ratio, is between 0 and 1, we know that the series converges, V sub n converges. That's just because it's a geometric series, and this ratio is between 0 and 1 on the absolute value, which in this case is positive, so that's the same thing. So since this is true, this function converges. And from the ratio test, because there is a limit of 1, then the whole thing converges. Now, I was just thinking about this one. There's probably a more satisfying way of looking at this. If you take this and you multiply both the numerator and the denominator by 3 to the minus n power, that limit becomes, you get 3 to the 0 power, which is 1, divided by 1 minus 5 times 3 to the minus n power. Okay, so in this case, when n goes to infinity, this goes to 0. 3 to the negative infinity is 0, and you just end it with 1. So here I just said, well, this number becomes insignificant, and therefore we just have these two terms. But if you multiply by 3 to the minus n power, you come to the same conclusion, but it's more obvious. Okay, next one, 19. Okay. So again, we're going to let a sub n equal this thing. And then we have to figure out a b sub n. And the requirements are that just that a sub n is greater than 0, b sub n is greater than 0. Obviously, it's just going to be greater than 0 because you have positive numbers, n is positive, so you don't have any subtractions. So that's true. And the question is, what can I do there to make it so that thing is, I can evaluate that limit. So I'm thinking about, it's like a p thing. So I could do it just like, there might be a better way of doing this, but let's say we just make it 2 to the n squared over 3n to the 5th power. This is also positive. If I take the limit as n goes to infinity of my original function, divided by my other function, like that. So again, we take the reciprocal. Okay. And if I divide each one of those by that, I'm going to get 1 minus 1 over 2 to the n squared here. And likewise, I can divide each one of these terms by that. And so I'll end up with 1 plus 2n over 3n to the 5th plus 1 over 3n to the 5th. And each one of these go to 0 and n goes to infinity. And so I just end up with 1. And so for the same reason, because this is equal to some value L, these two functions a and b are positive. And so the question is now, so that's true. Now we have to prove that this thing is going to have so if I look at the second series, I have to prove that that converges now. So I've got that, so I take the summation from n equals 1 to infinity of that, which is 2/3 times 1 over n cubed. So this is a p-type. So I have n to some power. And so this converges. So this series converges because p is greater than 1. And if you want to check that out, you can go back to the previous section, look under p-type, and it says if you have 1 over n to the p, if p is greater than 1, it converges. So this converges because p is greater than 1. And so since this converges and this has a limit, then this function also converges. Since p converges, therefore a sub n converges according to the, what do we call this test? The limit comparison test. So again, what I did is I took my original series, this is the term of each term of the series. I came up with this other function, which is just the highest order terms, b sub n. I took this ratio of the two, a sub n over b sub n. So instead of dividing by this, I multiplied by the reciprocal. Then I took this, and I divided every term here by that. So that became 1, and that became 1 over negative 1 over 2 n squared. Likewise here, this became 1. These terms go to 0 and n goes to infinity because I've got a constant in the numerator, except for that one, but I can, when I simplify it, I'll end up with n to the 4th in the denominator. So I ended up with a constant in the numerator and n in the denominator, and so these all three go to 0, so I ended up with the limit of 1. And so if this has a limit, this ratio of a sub n to b sub n has a limit of some limit as n goes to infinity, then if I can prove that b sub n converges, then according to the limit comparison test, then the original function also converges. So let's just check the answer on that one. Since it's an odd number. So this is chapter 9, section 4. Converges. Okay, so I got the right answer. Don't know if I did it right, but I'm pretty sure I did. Okay, let's go ahead and stop there, and we'll do another video for the next couple. Okay, so we're continuing on with our limit comparison test problems. So we've done 16 and 19. Let's do 22 and 25. Okay, so that's our original problem. So then you could take a function that looks like this, but is positive. Well, that's not hard. This actually, we could just multiply it out. So we get 1 over n cubed plus n. So I would think a good choice for the other series would be 1 over n cubed. So if we take the ratio, we take the limit as n goes to infinity of a sub n divided by b sub n So we take the term in the denominator and we take the reciprocal of that, like that. So what we're going to end up with is 1 over 1 plus n divided by n cubed. What I'm doing here is I'm multiplying by 1 over n cubed and multiplying by 1 over n cubed. So this goes to 1. And so this one, you get n cubed divided by n cubed, which is 1, and you get n divided by n cubed. You have to take the limit as n goes to infinity. What's happening, this goes to 0. So we just end up with 1. That's our limit. So again, we have to, if we can prove that B sub this series converges, which it does because it's a p-type, and p is greater than 1, therefore it converges. And so if this converges, then this converges because the ratio of these two terms was a limit. And it converges due to the limit comparison test. Okay, we have 25. So what we're looking at here is if k is greater than 2, let's just look at an example. Let's try k equals 3 and see what it looks like. We'll get n squared divided by n cubed plus 1. So it looks like, again, you could just do n cubed, n squared over n cubed, and you would get, you end up ultimately getting 1 over n, which actually does not converge. So, okay, so I think this is actually a case where it doesn't converge. So let's, so this is going to be a, actually we need to do this kind of for general. So I just wanted to look at it and see if I figured out what it would be. I think it's not going to converge. So let us, let's say, so a sub n is n to the k minus 1 over n to the k plus 1. So my b sub n is going to be n to the k minus 1 over n to the k, which ultimately becomes 1 over n. So if I subtract this from that, I'll get into the first power. Okay, so that's ultimately what I look at the convergence of, is this function, which is 1 over n. So what you do is you take the ratio. So you take the limit as n goes to infinity of n to the k minus 1 over n to the k plus the number 1 divided by n to the k minus 1 over n to the k. And again, we can take this and multiply by the reciprocal. So we're going to get n to the k minus 1 here and n to the k there. Those cancel out. And then if I multiply by 1 over n to the k in both the numerator and the denominator, And so what happens is we get 1 over 1 plus 1 over n to the k power. Okay, and that equals, when you let n go to infinity, this goes to 0 and you get 1. So it does equal the limit, but the other series, b sub n equals 1 to infinity, which equals the summation of n equals 1 to infinity of 1 over n, does not converge. Because the exponent, it's a p-type, the exponent is equal to 1. If we go back to the p-type thing, you'll see that it works if p is greater than 1, but it's equal to 1. It does not converge because p equals 1. So since this diverges the original series, also diverges, which is this one right there. Okay, so we're going to look in the answer back of the book. And that's 25, and it says diverges. Yes, okay. Okay, well, got a few more problems here in section 9.4. We're trying to, we need to figure out which test to use to solve these problems. And we have the nth term test, the p-series test, the integral test, limit comparison test, geometric series test, telescoping series test, and the direct comparison test. Okay, so those are the things that we know so far. And we said we're going to do 30 first. So we have summation from n equals 0 to infinity of 5 times negative 1/5 to the n. So that looks like a geometric series to me. And if we go back and look at a geometric series, the rule says so geometric series is in section 2. And it says if r, the ratio is between, absolute value of r is between 0 and 1. So r is negative 1/5. So r, the absolute value of r, is between 0 and 1. Therefore, the series converges. So first thing you have to do is recognize it's a geometric series. Once you do that, then you identify r, then you take the absolute value, see if it's between 0 and 1. If it does, then the series converges. Okay, 33. And you might be able to use more than one test, so if you say, oh, could I use that? Probably. Okay, so you could use the direct comparison test. In this case, because if I let b sub n be n over 2n, then this one is always greater than that one, and I get 1/2. And if I keep adding 1/2 up, then I end up with something that doesn't converge. So, and the other thing is that, yeah, that's the other part. So we don't actually use that. We can just use the nth term test that says that if you take the limit of a sub n as n goes to infinity, that has to at least equal 0 to have a chance. And so since the limit as n goes to infinity of 2n over 2n plus 3, that's going to be equal to a half because I have the same order term here. So you take the leading coefficients, and since that does not equal 0, it diverges. So that's the one test that tells you whether it diverges or not. So if it diverges, it's obviously not going to converge. And 36, we have summation n equals 1 to infinity of 3 over n times n plus 3. So I think you can actually use two methods to show this one's true. You could just multiply out the terms. So you get 3 over n squared plus 3n. So our given series terms are represented by this equation. So if you take, since this is positive, we know we can do a simpler version, which just has n squared, 3 over n squared. So if this converges, then that converges. And they're always positive. So I think this is the direct comparison test that we learned in this chapter. Yeah, so this is always less than that. So if this converges, then that converges. So what we need to do is look at the convergence of this series. And this is a p-series test. So this converges because it is a p-series and p is greater than 1. It's 2. So since our B series converges and A sub n is always less than B sub n, A sub n series converges. Now, I think you could also do the ratio if you wanted to, and you'd come to the same conclusion.